Welcome to the ARM School programme. This video is taken from our teacher training programme on edX.org called Teaching with Physical Computing. Whether you're new to teaching computing or a specialist, this programme will set you up on a path to becoming an expert in delivering technology-enabled project-based learning in the classroom. This module explores the links between computational thinking and project-based learning and how project-based learning can make learning computational thinking more engaging.
In this module on computational thinking, we're going to explore the various cornerstones of computer science. We are going to identify what abstraction, decomposition, algorithms, data, problem-solving and debugging are, and how they are used within a project-based learning or PBL approach. Abstraction is the removal of unnecessary detail from a problem. It allows you to focus on the core problem, which makes it easier to solve. We are now going to have a look at how the concept of abstraction can be applied to the development of a racing car game. First of all, let's look at a photograph of a race circuit. We can see lots of detail in the photograph. There is the main track. There are markings on the track. There are various buildings, there are trees, and there are advertising signs, as well as a range of other features. If we were to focus on all these different features and incorporate them into the game at once, then just designing the look and feel of the circuit would be quite a complex task. It is therefore useful to apply abstraction to this problem. If we think about the core features of the track, we can identify the track itself, the shapes of the corners, and the fact that it is surrounded with grass and trees. All other features can be ignored at the moment without any impact on developing the track for our game. As you can see, applying abstraction to this process allows us to get to the heart of the problem, which is developing the track itself with corners of the correct shape. We are now going to look at decomposition. Decomposition allows us to break down the overall problem into a number of sub-problems. Let us take the analogy of our car racing game. If we think about the overall game, there are clearly a number of sub-tasks within it, all of which we need to complete in order to make a successful game. We need to develop a main menu from which users can access various options. We need to develop a method of controlling the cars. We need to build the track that the cars will drive around. We need to develop competitor cars. We also need to develop a scoring system. Algorithms can be planned for each sub-problem. Then they can be coded, tested, and added to the overall solution. One of the key benefits of applying decomposition is that any problems you identify can be solved early, rather than only being identified late in the development process. When we plan a solution in computer science, we use an algorithm. An algorithm is a list of step-by-step instructions which, when followed, solve a problem. Algorithms can be represented using either flowcharts or pseudocode. Younger students tend to find flowcharts more straightforward, whereas older students tend to be more confident when writing pseudocode, as this is closer to how they will actually implement the algorithm. It is important to stress that an algorithm is not code. The way that we implement the algorithm is by writing code. Successful algorithms have a few key features. They should be completed in as few steps as possible so that the solution is efficient. They should always produce the correct output for any set of valid inputs. They should also be able to handle erroneous inputs. They should also always terminate at some point. When students first start writing algorithms, they often overcomplicate their solutions, thus making them inefficient. While this is unlikely to be a big issue at school, efficiency is extremely important when it comes to processing large amounts of data, so it is worth emphasizing this to students. From the flowchart that we looked at in the previous section, we know that a process is required to turn an input into an output. You can therefore see that there is a direct link between computational thinking and the Input Process Output, or IPO model, both of which underpin the PBL approach. Data is taken as an input. It is then processed according to the algorithm, and then the algorithm produces an output. Data itself has no context or meaning. Computers will simply process the data according to the instructions that they are given. One of the key areas of computational thinking is the ability to debug a program. Debugging means identifying errors in the code and fixing them. Three main types of error can appear in code. The most difficult to identify is often a logic error. If there is a logic error, this means that the code produces an unexpected output. As far as the computer is concerned, there is no issue with the code. This is what makes it difficult to identify, as it is down to the human to find out where the error is in the code. The second type of error is a syntax error. This is where the code doesn't meet the rules or grammar of the language. This type of error is easier to identify as an integrated development environment (IDE) will highlight where the error has been caused. The human then just needs to correct that line of code so that it does follow the rules of the language. When there is a syntax error, the code will not run at all. Many students find the whole area of computational thinking difficult to understand when it is delivered in purely theoretical concepts. Covering the area using PBL makes it far more accessible to students.
To learn more, head over to edX.org and search for project-based learning and enrol for free.